Hello, friend. Welcome back. Or perhaps welcome for the first time. Either way, I'm glad you're here. Some nights the sky feels heavier than it should. Stars breathe slower. Time folds in on itself, quiet and still. Maybe that's just the mind listening to the universe whisper back. Tonight we're going to drift beyond the last stars, beyond the final glow of light, into a future so distant that even time might forget how to count. We're going to talk about black dwarfs, objects that don't exist, yet objects that won't exist for trillions upon trillions of years. Objects born from the last breath of dying stars, when even embers forget how to shine. Before we begin this long, quiet journey together, if you find comfort in these nocturnal wanderings, you might like to stay a while. You can gently tap the like button, not for the algorithm, but as a small signal that you're here listening in the dark with me. Subscribe if you'd like more stories told softly under distant stars. And ring the little bell not for noise, but so the next quiet night can find you again whenever you need it. These small gestures help this channel reach others who might need a gentle voice in the stillness. Thank you for that kindness. Now, let's drift. Imagine the last light in the universe. Not a supernova, not a brilliant death scream across the cosmos. Just a faint glow barely warm enough to disturb the surrounding void, slowly cooling, fading until one day, perhaps billions of years from now, perhaps quadrillions, it simply stops. No flash, no sound. Just silence settling like snow. That's a black dwarf, the final period at the end of a star's long, patient sentence. You see, most people think of stellar death as dramatic. We picture supernovas, neutron stars, spinning madly black holes devouring light itself. And those things happen, yes, but only to certain stars, the massive ones, the giants who live fast and bright. For the vast majority of stars, the ones like our sun, death is quieter, slower, almost meditative. They don't explode, they exhale. Our sun, for instance, will one day swell into a red giant, swallowing Mercury, Venus, perhaps even Earth. It will shed its outer layers like an old coat, revealing a hot, dense core beneath a white dwarf. Scientists suggest this will happen in about 5 billion years. 5 billion. That sounds like forever, doesn't it? But in the life of the universe, it's just a heartbeat. White dwarfs are strange, beautiful things. They're roughly the size of Earth, but packed with about half the mass of the sun. A teaspoon of white dwarf material would weigh as much as an elephant here on Earth. They glow not from fusion like living stars, but from leftover heat slowly radiating into space. They shine in infrared, then red, then dimmer, still like coals in a fireplace, gradually losing their warmth. And here's the thing, they don't stop glowing quickly. It takes an unimaginable amount of time for a white dwarf to cool completely. How long research shows somewhere between 10 quadrillion and 100 quintillion years. To put that in perspective, the universe is currently about 13.8 billion years old. If the universe's entire history so far were compressed into a single second, a white dwarf would need trillions of years, trillions to become a black dwarf. We're talking about timescales so vast that human language barely has words for them. Numbers that make infinity feel close, almost friendly. Black dwarfs, then, are the final form, the end state. When a white dwarf has radiated every last bit of its stored heat into the void, when it has cooled to the temperature of the surrounding space, it becomes a black dwarf. No light, no warmth, just mass sitting quietly in the dark, holding its shape through sheer stubbornness. It's the stellar equivalent of a memory, something that once burned bright, now resting in stillness. Here's something most people get wrong. Black dwarfs are not black holes. It's an easy mistake to make both have black in the name, both sound ominous. But they're almost opposites. A black hole is a point of infinite density, a place where gravity is so strong that not even light can escape. It crushes, consumes, warps space-time itself. A black dwarf, on the other hand, is simply cold. It doesn't pull, it doesn't crush, it just is. quietly existing, no longer participating in the universe's great dance of energy and light. One devours, the other simply stops. And here's the truly humbling part. No black dwarf has ever existed. Not one. Not anywhere in the universe. The cosmos simply isn't old enough yet. Every white dwarf we've ever observed is still glowing, still radiating heat, still clinging to the last remnants of its stellar life. Even the oldest, coldest white dwarfs we know, ancient stars that have been cooling for billions of years, are still too young, too warm to qualify. They're still white, not black, still holding on to their faint glow, like a candle refusing to go out. Consider WD0346 plus 246, one of the coldest white dwarfs ever discovered. Its surface temperature is estimated at around 3,900 Kelvin. That might sound hot, it is hot by human standards, but for a stellar remnant, it's positively frigid. It's been cooling for billions of years, and yet it still glows faintly in infrared, still warm, still alive in its own quiet way. Even this ancient ember hasn't reached the stillness of a black dwarf. The universe simply hasn't had enough time. Think about that for a moment. The universe has existed for nearly 14 billion years. Stars have formed, lived, died. Galaxies have collided, merged, drifted apart. Planets have been born and destroyed. Life has emerged at least once. And yet in all that time and all that cosmic history, no star has ever fully completed its journey to become a black dwarf. We live in a universe that is in some profound sense still young, still in its stellar adolescence. What does it feel like to contemplate such time scales? Sometimes I think our minds aren't built for this kind of thinking. We're creatures of seasons of sunrises and sunsets of years and decades. A human lifetime is roughly 80 years if we're lucky. A century feels long to us. A millennium feels mythical. But a quadrillion years, a quintillion. These aren't just big numbers, they're almost meaningless to our pattern-seeking brains. They stretch beyond comprehension, beyond metaphor. And yet, they're real. As real as the ground beneath your feet. Black dwarfs belong to a future so distant that the universe we know will be unrecognizable. All the stars you see in the night sky, gone. The Milky Way galaxy dispersed or merged with Andromeda into a massive elliptical galaxy that itself will eventually go dark. The cosmic microwave background radiation, that faint afterglow of the Big Bang, stretched and redshifted into nothingness by the universe's expansion. Everything familiar, everything we use to orient ourselves in space and time will have faded. And in that deep, cold future, black dwarfs will drift alone, silent monuments to a universe that once blazed with light. Some scientists call this era the degenerate era, the time when stellar remnants, white dwarfs, neutron stars, black holes are the only objects left. It comes after the stelliferous era, the current age of stars. We're living in the age of light, the age of fusion, when stars are still being born, in nebulae, still shining, still warming planets. But that won't last forever. Star formation will eventually cease as the universe runs out of hydrogen the fuel stars need. The last stars will flicker out. And then silence. But even in that silence, something persists. Black dwarfs will still be there carrying the memory of what stars once were. They'll be composed mostly of carbon and oxygen, the ashes of helium fusion locked into a crystalline lattice. Imagine that a sphere the size of Earth made of crystal, colder than the void around it, drifting through space like a forgotten jewel. No one to see it, no light to catch its facets, just existence for its own quiet sake. Is there something comforting in that? Maybe. Maybe it's the universe's way of showing us that even endings have their own dignity. That even when the fire goes out, the shape remains. That stillness isn't the same as nothingness. We're only beginning this journey. There's so much more to explore, the physics of how stars cool, the mystery of crystallization inside white dwarfs. the strange mathematics of deep time, the final fate of matter itself. But for now, just rest in this idea somewhere in a future so far away, it might as well be imaginary. There will be stars that have forgotten how to shine. And they'll be beautiful in their own way. Beautiful because they endured. Beautiful because they lasted. Beautiful because they simply are. The universe doesn't demand that we understand it, only that we witness it quietly, with whatever wonder we can muster. And tonight you're doing exactly that. So, thank you. Thank you for drifting with me into these deep, cold places where time moves differently, where light is just a memory, and where the stars have learned the art of stillness. We have so much further to go together, down into the mechanisms of forgetting, into the heart of what makes a star surrender its warmth. The physics, the poetry, the math, it's all waiting just ahead in the dark. To understand where black dwarfs come from, we need to trace their lineage back through time, back through the generations of stellar evolution. Every black dwarf has ancestors, brilliant burning ancestors that lived for billions of years before cooling into silence. Think of it as a family tree, but instead of people, we're mapping the lives of stars. And like any family history, it's full of transformations, quiet tragedies, and moments where everything changes. Stars are born in clouds, vast cold nebulae where gas and dust collapse under their own gravity, spinning faster, heating up until at the core, pressure and temperature rise high enough for fusion to begin. Hydrogen atoms slam together, forming helium, releasing energy, light, heat, the stuff that makes a star shine. This is the main sequence, the long, stable phase of a star's life. Our sun has been on the main sequence for about 4.5 billion years, and it has roughly another 5 billion to go. For most of that time, nothing dramatic happens. The star just burns steady and patient, converting hydrogen into helium in its core, radiating warmth into space. But eventually, the hydrogen runs out. Not all at once, stars don't suddenly flicker and die like candles in the wind. Instead, the core contracts, heats up, and begins fusing helium into heavier elements, carbon, oxygen. The outer layers, meanwhile, expand outward, swelling into a red giant. The star grows enormous, hundreds of times its original size, cool and bloated, glowing a deep burnt orange. Scientists suggest that when our sun reaches this stage, it will extend past the orbit of Mars. Mercury will be consumed, Venus too. Earth's fate is uncertain. Some models say we'll be swallowed, others suggest we'll survive, scorched and lifeless, drifting in the red giant's outer atmosphere. Either way, nothing will remain of the world we know. This is the second chapter in the stellar family tree, the red giant phase. It's shorter than the main sequence, only a few 100 million years for a sun-like star, but it's transformative. The star sheds its outer layers in slow pulsing waves, creating beautiful structures called planetary nebulae. These aren't related to planets despite the name. Early astronomers just thought they looked planet-like through their telescopes. In truth, they're shells of glowing gas lit from within by the hot core of the dying star. The Ring Nebula, the Helix Nebula. These are the ghosts of red giants, monuments to stars that once were. And at the center of each planetary nebula, there's a remnant, a white dwarf. This is the third stage, the penultimate chapter. The red giant's core now exposed, no longer fusing elements, just radiating stored heat. It's incredibly dense, about half the mass of the sun, compressed into a sphere roughly the size of Earth. To put that in perspective, if you could take a sugar cube-sized piece of white dwarf material and bring it to Earth, it would weigh about a ton. A single ton compressed into something you could hold in your hand. The atoms are packed so tightly that normal matter rules no longer apply. Electrons are squeezed into the smallest possible spaces, creating something called electron degeneracy pressure, a quantum mechanical effect that prevents the star from collapsing further. It's not heat or fusion holding the star up anymore. It's pure quantum physics, the universe saying, this far and no farther. White dwarfs glow because they're hot. When they first form their surface, temperatures can exceed 100,000 Kelvin. That's hotter than the surface of most main sequence stars. But they're not generating new heat. They're just slowly losing the heat they accumulated over billions of years of fusion. They cool by radiation, emitting light across the spectrum, ultraviolet, visible, infrared. And eventually, when they've cooled enough, they'll emit almost nothing at all. Research shows that the coolest white dwarfs we've observed have surface temperatures around 3,000 to 4,000. Kelvin, still warm by human standards, but cold for a star. They glow a deep, dull red, barely visible even with powerful telescopes. The most famous white dwarf in our neighborhood is Sirius B, the companion to Sirius, the brightest star in Earth's night sky. Sirius B orbits Sirius A, a main sequence star about twice the mass of our Sun. Sirius B was discovered in the mid-19th century, not by seeing it directly, but by observing the wobble in Sirius A's motion, evidence that something massive but invisible was tugging on it. When astronomers finally observed Sirius B directly, they were astonished. It was faint, incredibly faint for something so massive. It didn't make sense until they realized what they were seeing: a white dwarf, a stellar corpse orbiting its younger, brighter sibling. Sirius B has about the mass of our Sun, but the radius of Earth. It's cooling slowly over billions of years, on its way to becoming a black dwarf, though it won't get there for an unimaginable stretch of time. Here's where people often get confused. They hear black dwarf and think black hole, as if they're related. It's an understandable mistake. Both sound ominous, both involve the word black. Both are stellar endpoints. But they couldn't be more different. A black hole forms when a massive star, at least 8 to 10 times the mass of the Sun, runs out of fuel and collapses catastrophically. The core implodes, and if there's enough mass, nothing can stop it. Not electron degeneracy pressure, not neutron degeneracy pressure, nothing. It collapses into a singularity, a point of infinite density, where the laws of physics as we know them break down. The gravity is so intense that space-time itself warps, creating an event horizon, a boundary beyond which nothing, not even light, can escape. Black holes don't just sit quietly. They pull, they warp, they consume. They're active, violent, hungry. Black dwarfs, by contrast, are the quietest objects imaginable. They don't pull anything in, they don't have enough mass for that. They don't emit light or heat. They don't warp space-time in any meaningful way. They just exist inert and invisible, supported by the same electron degeneracy pressure that holds up white dwarfs. They're the remnants of stars too small to become black holes. Stars that ended their lives not with a supernova, but with a gentle exhalation. One crushes, one simply stops. It's the difference between a collapse and a rest. Another common misconception: some people think white dwarfs might reignite, might somehow start fusing again and return to life. It's a comforting thought, isn't it? The idea that stars might get a second chance. But it doesn't work that way. Once a star has shed its outer layers and become a white dwarf, fusion is over. There's no more hydrogen in the core. And even if there were, there's no mechanism to restart it. The core is too dense, too degenerate. The electrons are packed so tightly that adding more heat doesn't change the pressure. It's quantum mechanics, not thermodynamics, keeping the star from collapsing. A white dwarf can accrete matter from a companion star, and in rare cases that can lead to a type 1, a supernova, a thermonuclear explosion that obliterates the white dwarf entirely. But that's not reignition, that's destruction. For most white dwarfs, especially isolated ones like the future version of our Sun, there's no companion, no fresh fuel, just slow, patient cooling. How long does that cooling take? We touched on this earlier, but it's worth repeating because the numbers are so staggering. A white dwarf with a mass similar to our Sun will take roughly 10 to the 15th years to cool to the temperature of the cosmic microwave background, the faint radiation left over from the Big Bang, currently about 2.7 Kelvin. That's a quadrillion years, 1,000 trillion. If you tried to count to a quadrillion one number per second, it would take you over 30 million years. And that's just to cool to the background temperature, not to absolute zero. To truly become a black dwarf, indistinguishable from the void around it, could take even longer. Some estimates suggest 10 to the 20th years. 100 quintillion. Numbers so large they feel almost fictional, like something out of a fever dream. But they're real. And in that distant future when the universe is cold and dark and the last stars have long since faded, black dwarfs will drift alone, silent, still, holding their shape not through heat or light, but through the stubborn insistence of quantum mechanics. They'll be composed mostly of carbon and oxygen, the ashes of helium fusion, arranged in a crystalline lattice. Imagine that a sphere the size of a planet, made of diamond-like crystal, floating in absolute darkness. No warmth, no glow, just mass enduring. Do you ever wonder what it would be like to encounter one? To float in the void near a black dwarf, to reach out and touch its surface. It would be colder than anything you've ever felt. Colder than deep space, which itself is only a few degrees above absolute zero. The black dwarf would be indistinguishable from the emptiness around it, invisible, a ghost. You'd only know it was there by its gravity, a faint tug pulling you gently toward its surface. And if you stood on that crystalline sphere, you'd be standing on the corpse of a star that once burned bright, that once fused hydrogen and helium, that once warmed planets, that once maybe sustained life. Now, just cold, just still, just memory frozen into carbon. There's something humbling in that isn't there. The idea that even the brightest things eventually rest, that light for all its beauty is temporary, that the universe's default state isn't brilliance but silence. And yet, even in that silence, there's a kind of dignity. The black dwarf doesn't cease to exist. It doesn't vanish. It endures quietly, patiently, long after the universe has forgotten what stars even were. It's a testament to persistence, to the idea that existence itself, even without warmth or light, has value. We're still tracing the family tree, still mapping the path from main sequence to red giant to white dwarf to black dwarf. And there's so much more to explore, the physics that governs this cooling, the mechanisms that allow a star to hold its shape even in death, the strange quantum rules that prevent total collapse. But for now, rest in the lineage. Rest in the knowledge that every black dwarf, though none exist, yet carries within it the memory of a star that once blazed. The journey from light to darkness is long, patient, inevitable, and we're only beginning to understand the steps along the way. Now, we descend into the mechanics of forgetting. How does a star once brilliant and blazing slowly release its warmth until there's nothing left? How does light fade into darkness, heat into cold memory, into stillness? The physics of cooling is quieter than the physics of burning, but no less profound. It's the science of letting go, one photon at a time. When a white dwarf first forms, it's searingly hot. Surface temperatures can reach 100,000 Kelvin, or more, far hotter than the sun's surface, which sits at a relatively cool 5,700 Kelvin. That heat isn't coming from fusion anymore. There's no more hydrogen burning in the core, no helium fusing into carbon. The nuclear furnace has gone dark. What remains is residual thermal energy, the leftover warmth accumulated over billions of years of stellar life. Think of it like a stone pulled from a fire. The fire's out, but the stone still radiates heat slowly, persistently, until it matches the temperature of the air around it. A white dwarf is that stone only. Instead of cooling over minutes, it cools over eons. The process is called thermal radiation. Every object with temperature emits electromagnetic radiation light, essentially, though not always the kind we can see. Hot objects emit high-energy photons, ultraviolet X-rays. Cooler objects emit lower-energy photons, visible light infrared radio waves. A freshly formed white dwarf glows intensely in the ultraviolet spectrum, invisible to the naked eye, but brilliant to instruments designed to detect it. Over time, as the dwarf cools, the peak of its radiation shifts downward, Ultraviolet gives way to blue, then white, then yellow, then red. Eventually, the dwarf cools enough that it emits primarily in the infrared heat you could feel if you were close enough, but not light you could see. And still, it cools. Infrared fades to microwave to radio to nearly nothing. Scientists suggest this cooling follows a predictable curve governed by the laws of thermodynamics. The Stefan-Boltzmann law tells us that the energy radiated by an object is proportional to the fourth power of its temperature. That means a white dwarf at 100,000 Kelvin radiates energy 10,000 times faster than one at 10,000 Kelvin. Early in its cooling, the dwarf sheds heat quickly, relatively speaking. But as it cools, the rate of energy loss slows dramatically. It's an exponential decay, a curve that approaches zero but never quite reaches it. Each passing billion years sees less heat lost than the billion before. Cooling becomes slower, quieter, more patient. But here's where it gets strange. A white dwarf doesn't cool the way you might expect. It doesn't radiate uniformly from its surface like a simple sphere of hot metal. Its internal structure matters. White dwarfs are layered like onions with different compositions at different depths. The outermost layer is typically a thin shell of hydrogen left over from the star's outer envelope. Beneath that is a layer of helium, the product of hydrogen fusion from the star's main sequence days. And deeper still at the core is a mix of carbon and oxygen, the ashes of helium fusion. These layers don't conduct heat uniformly. The hydrogen and helium layers act as insulation, slowing the escape of thermal energy from the carbon-oxygen core. It's as if the star wrapped itself in a blanket before dying, preserving its warmth a little longer. This layered structure means that even as the surface cools, the core remains hot for an extended period. Heat diffuses outward slowly, limited by the thermal conductivity of the degenerate matter inside. Degenerate matter is peculiar stuff. It's not a gas, not a liquid, not a solid in the traditional sense. It's matter compressed to such density that quantum mechanics dominates. Electrons are packed so tightly they occupy the lowest possible energy states, and the rules of classical physics no longer fully apply. In this state, heat doesn't flow easily. The core can remain millions of degrees Kelvin even as the surface drops to tens of thousands, then hundreds. The dwarf cools from the outside in like a cooling ember, the glow retreating inward until only the very center holds any warmth. Research shows that this cooling process is also influenced by something called neutrino emission. Neutrinos are ghostly particles nearly massless with almost no interaction with matter. They are produced in certain nuclear reactions and simply pass through most material as if it weren't there. In a cooling white dwarf, neutrinos are generated in the core through various quantum processes, and they escape the star, almost immediately carrying away energy. Unlike photons, which can take thousands of years to diffuse from the core to the surface, neutrinos leave instantly. This makes neutrino cooling extremely efficient in the early stages, when the core is still hot enough for these reactions to occur. But as the temperature drops, neutrino emission slows and eventually stops. Photon radiation takes over as the dominant cooling mechanism, and the process slows further still. One of the coldest white dwarfs ever studied is WD 0346+246, which we mentioned earlier. Its surface temperature is estimated at around 3,900 Kelvin, cool enough to glow a deep red, barely visible even with powerful telescopes. It's located roughly 87 light-years from Earth, a relatively nearby stellar corpse. Observations suggest it has been cooling for approximately 11 billion years, making it one of the oldest known white dwarfs in our galaxy. And yet, despite all that time, it's still radiating heat, still glowing faintly in infrared, still far, far warmer than the cosmic microwave background, which sits at a chilly 2.7 Kelvin. It has quadrillions of years left to cool before it could be considered a black dwarf. Another fascinating example is the white dwarf PSRJ 0348 plus 0432. Though this one is part of a binary system, it orbits a pulsar, a rapidly spinning neutron star. Astronomers have measured its mass at about twice that of our Sun, making it one of the most massive white dwarfs known. Its surface temperature is estimated at around 11,000 Kelvin, still quite hot by white dwarf standards. What makes it interesting is that its companion pulsar allows scientists to test general relativity with extraordinary precision. The two objects orbit each other so closely that space-time itself warps. And by measuring the orbital decay, how the orbit shrinks over time, due to gravitational wave emission, astronomers can confirm Einstein's predictions. But from a cooling perspective, this white dwarf is still in its infancy. It's still bright, still warm, still billions of years away from the darkness we're contemplating. Here's something people often misunderstand. Cooling doesn't mean the star is losing mass. A white dwarf's mass remains essentially constant throughout its cooling phase. It's not evaporating or sublimating into space. The energy it radiates is thermal energy, not matter. The photons escaping into the void carry energy. Yes, but they don't carry significant mass. Einstein's equation, E equals mc squared, does imply a tiny mass loss, but it's negligible over even cosmic timescales. A white dwarf cooling from 100,000 Kelvin to 3,000 Kelvin loses an infinitesimal fraction of its mass. For practical purposes, it stays the same size, the same mass, the same density. Only its temperature changes, only its glow fades, and that glow is worth contemplating. Imagine watching a white dwarf over billions of years time-lapse style. At first, it shines bright blue, almost blinding in its intensity. Over the first 100 million years, it shifts to white, then pale yellow. After 1 billion years, it's orange like a setting sun. After 10 billion, it's deep red, ember-like, fading. After 100 billion years, 7 times the current age of the universe, it's barely visible, a dark crimson glow, detectable only by the most sensitive instruments, and still it cools. After 1 trillion years, it's invisible to optical telescopes, radiating only in the infrared. After 1 quadrillion years, even that infrared glow is nearly gone. The star has become a shadow of a shadow, a memory held in the structure of atoms too stubborn to collapse. What prevents that collapse? Why doesn't a white dwarf simply shrink down to nothing as it cools? This is where electron degeneracy pressure comes, in a concept we touched on before, but it deserves deeper attention. In normal matter, atoms are mostly empty space. Electrons orbit nuclei at relatively vast distances, and there's room to compress things if you apply enough pressure. But in a white dwarf, gravity has already compressed the matter to extraordinary density. Electrons are squeezed into the smallest possible volume, and quantum mechanics steps in with a firm rule: no 2 electrons can occupy the same quantum state. This is the Pauli exclusion principle, one of the fundamental laws of the quantum world. It means that even when all thermal pressure is gone, even when the star is cold and dead, the electrons resist being compressed further. They push back not because they're hot, but because the universe's quantum rules forbid them from occupying the same space. This degeneracy pressure is what holds up a white dwarf, and later, a black dwarf. It's not heat, it's not motion, it's pure quantum stubbornness. Think about that for a moment. A black dwarf in the far future, cold as the void around it, is held up by nothing but the Pauli exclusion principle. Gravity pulls inward with relentless patience, but the electrons refuse to yield. It's a stalemate that lasts forever, or at least as close to forever as the universe allows. The star doesn't collapse, doesn't explode, doesn't change. It just is suspended in quantum defiance, a monument to physical law. There's a certain poetry in that, don't you think? The idea that even in death, even in absolute cold, the universe maintains structure. That matter remembers its rules even when there's no energy left to enforce them. That a star can die and still hold its shape not through fire or light, but through the invisible architecture of quantum mechanics. It's as if the universe refuses to let things dissolve completely into chaos. There's an order, a stubbornness, a refusal to surrender form even in the face of entropy. But entropy does win slowly. Heat spreads, thins, dissipates. The white dwarf radiates its warmth into the expanding void, and that energy is lost forever, redshifted and diluted until it's indistinguishable from the cosmic background. The star gives and gives patiently over incomprehensible spans of time until it has nothing left to give. And then it rests, not in nothingness, but in stillness. A cold, dense sphere drifting through space supported by quantum rules older than stars themselves. We've explored the mechanisms: thermal radiation, neutrino, emission, electron, degeneracy. We've seen examples of the coolest white dwarfs we know, ancient objects still clinging to their faint glow. We've contemplated the time scales, the laws, the slow surrender of warmth into the dark. But there's something else happening inside these cooling stars, something beautiful and strange that we haven't touched on yet. As the temperature drops and the atoms slow, a transformation begins. The disordered plasma of the star's interior starts to organize itself atom by atom into something crystalline, something almost magical. And that's where we drift next into the mystery of what happens when a star becomes a jewel. Inside a cooling white dwarf, something extraordinary begins to happen. Something that sounds more like alchemy than astronomy. As the temperature drops and the chaotic plasma settles, the carbon and oxygen atoms at the star's core start to arrange themselves into a lattice, a crystalline structure. The star in its slow death transforms into something resembling a gemstone, a diamond, the size of Earth floating silently in the void. It's not a metaphor, it's physics, and it's one of the most beautiful transformations in the cosmos. For decades, this was purely theoretical. Scientists had long suspected that white dwarfs would crystallize as they cooled, based on models of how matter behaves under extreme pressure and decreasing temperature. But suspicion isn't proof. The confirmation came in 2019 when astronomers analyzed data from the Gaia Space Telescope, which had been measuring the brightness and positions of over 1 billion stars in our galaxy. Among those stars were roughly 15,000 white dwarfs. And when researchers plotted their luminosities against their colors, essentially mapping their temperatures and brightness, they noticed something peculiar. There was a pileup in excess of white dwarfs at certain temperatures, more than statistical models predicted. The data suggested that these stars were cooling more slowly than expected, as if something inside them was releasing extra energy. That something scientists suggest was crystallization. When a liquid freezes into a solid, it releases latent heat. This is a basic principle of thermodynamics. Water, for instance, releases energy when it turns to ice, which is why freezing water warms its surroundings slightly. The same principle applies to white dwarfs. As the carbon and oxygen ions in the core slow down and lock into a crystalline lattice, they release energy heat that temporarily slows the star's cooling. Research shows this process can delay the cooling by as much as 1 billion years or more, depending on the dwarf's mass and composition. It's as if the star in its final act finds one last reservoir of warmth hidden in the structure of its own atoms. The process begins at the center of the white dwarf, where the pressure is highest and the temperature paradoxically drops first as heat radiates outward. The core reaches the critical point where the thermal energy of the ions, the random jiggling and vibration, is overcome by the electrostatic forces between them. They want to arrange themselves into an orderly pattern, like dancers finding their places on a stage. Carbon and oxygen ions, stripped of most of their electrons by the intense pressure, settle into a face-centered cubic lattice, the same crystalline structure found in diamonds here on Earth. The difference is one of scale and purity. A white dwarf's crystal isn't a small gem you could hold in your hand. It's a sphere thousands of kilometers across a planetary mass of ordered carbon and oxygen, locked into place by quantum pressure. The most famous example, though, it's not a white dwarf in the traditional sense, is BPM 37093, A star, affectionately nicknamed Lucy, after the Beatles' song Lucy in the Sky with Diamonds, located about 50 light-years from Earth in the constellation Centaurus. Lucy is what's called a pulsating white dwarf. It vibrates ringing like a bell, and by studying those vibrations, asteroseismology, the science of stellar earthquakes, astronomers can peer inside the star and infer its internal structure. Research suggests that roughly 90% of Lucy's mass has crystallized into carbon. It's a diamond star, a cosmic jewel weighing about 5 billion trillion carats. If you could somehow mine it, the value would be well meaningless. There's no economy that could absorb that much diamond. It would make the material worthless. But the beauty isn't in the value, it's in the existence. A star transformed by time and pressure into something crystalline and eternal. Here's something most people get wrong. They assume the entire white dwarf crystallizes all at once like water, freezing into a solid block of ice. It doesn't work that way. Crystallization begins at the core and spreads outward slowly over millions or even billions of years. The outer layers of the star remain liquid, or rather in a plasma state, while the inner regions solidify. It's a gradual transformation, a freezing front that moves outward as the star continues to cool. Eventually, if given enough time, the entire star will crystallize from the core to just beneath the thin hydrogen and helium envelope on the surface. But that takes an immense amount of time, far longer than the current age of the universe. Most white dwarfs we observe are only partially crystallized, if at all. They're caught in the middle of the process, halfway between liquid and solid star and stone. The crystalline structure itself is fascinating. In a diamond, carbon atoms are arranged in a tetrahedral lattice, each atom bonded to 4 neighbors in a 3-dimensional network. This gives diamond its incredible hardness and its ability to refract light into brilliant colors. In a white dwarf, the lattice is similar, but the conditions are far more extreme. The pressure at the core can reach millions of atmospheres, pressures that would crush any material we know into powder. And yet, the crystal holds. The ions are locked in place not by chemical bonds in the traditional sense, but by a combination of electrostatic repulsion and quantum mechanical effects. The electrons stripped away and existing in a degenerate state form a sea of negative charge that permeates the lattice, screening the positive ions from each other just enough to prevent collapse. It's a delicate balance, a structure maintained by forces operating at the smallest scales of reality. One detail worth noting, the crystallization doesn't happen uniformly across all white dwarfs. The composition matters. White dwarfs with higher carbon content crystallize differently than those with more oxygen. Some models suggest that in certain cases, the carbon and oxygen might separate as the star cools, with heavier oxygen sinking toward the center and lighter carbon rising toward the surface. This would create a layered structure, an onion of different crystalline phases, each with its own properties. Other models suggest mixing with carbon and oxygen ions interspersed throughout the lattice. The truth likely depends on the star's mass cooling rate and initial composition variables that differ from star to star. Every white dwarf, in a sense, crystallizes in its own unique way. There's also the question of impurities. Real diamonds on Earth often contain trace amounts of other elements, nitrogen, boron, hydrogen, that give them color and affect their properties. A white dwarf's crystal is mostly carbon and oxygen, but there are trace amounts of heavier elements: neon, magnesium, silicon, iron. These were produced in the star's core during its red giant phase, when helium fusion briefly created heavier nuclei. As the star crystallizes, these impurities get trapped in the lattice, embedded like inclusions in a gemstone. Do they affect the structure? Do they create flaws, stress points, regions where the crystal is weaker or denser? Scientists suggest yes, though the details are still being worked out. The crystal isn't perfect. It has defects, dislocations, boundaries where different crystalline grains meet. It's a frozen chaos ordered, but not pristine. Imagine holding a fragment of that crystal in your hand if such a thing were possible. It would be impossibly heavy. A single cubic centimeter would weigh roughly a ton. It would be colder than anything you've touched its surface, smooth and featureless, reflecting no light, because there's no light to reflect in the void where it formed. And if you could somehow look inside, peer into its atomic structure, you'd see a lattice stretching on for kilometers, billions upon billions of carbon and oxygen ions locked in perfect geometric harmony, a structure that took a star's lifetime to create, a lifetime measured in billions of years. And this crystal, this jewel born from fusion and time, will endure long after the universe has gone dark. It's a kind of immortality, isn't it? Not life, not consciousness, but persistence. Form holding against entropy. There's a lesson hidden in this, though maybe lesson is the wrong word. An observation, perhaps. The universe has a tendency to create order out of chaos, given enough time and the right conditions. A cloud of gas collapses into a star. A star fuses hydrogen into helium into carbon and oxygen. And when the fusion stops, when the heat fades, those atoms don't just scatter. They organize, they crystallize, they become something structured, something beautiful in its own quiet way. It's as if matter left to its own devices seeks patterns, seeks stability, seeks form. And yet this crystallization is just one phase in the star's long journey toward becoming a black dwarf. The crystal itself will continue to cool. The lattice will remain held in place by quantum forces, but the temperature will drop. The faint infrared glow will fade. The star will darken until it's indistinguishable from the void. But inside the structure persists. The diamond remains unseen, unlit, a testament to what the star once was. Do you think there's beauty in that? In something existing without being witnessed? In a jewel that will never catch the light, never be admired, never be known, except through the abstractions of physics and mathematics? Some might find it sad, the idea of such beauty going unseen, but maybe that's a human bias, the need for witness, for validation. The white dwarf doesn't care. It doesn't need to be seen. It simply is crystallizing slowly in the dark, following the laws that govern all matter, all energy, all structure. And in that indifference, there's a kind of purity, a kind of peace. We've traced the transformation from plasma to crystal, from chaos to order. We've seen how a star in cooling releases one last breath of warmth through the act of freezing. We've contemplated the structure, the scale, the imperfections and inclusions that make each crystallized dwarf unique. But all of this, the cooling, the crystallization, the slow march toward darkness, happens against a backdrop of time so vast, it defies comprehension. And that's where we turn next, into the deep hours of the cosmos, into the patience required to watch a star forget itself completely. The clock is ticking, but so slowly you'd need 1 trillion years just to hear a single second pass. Time at cosmic scales stops meaning what we think it means. 1 billion years becomes a blink. 1 trillion years becomes a breath. And the time scales required for a white dwarf to become a black dwarf. Those aren't just long, they're incomprehensible. They stretch beyond human intuition, beyond analogy, into a realm where numbers lose their weight, and only the mathematics remains solid. Tonight, we're going to sit with that discomfort. We're going to let deep time wash over us, not to understand it, because we can't, not really, but to feel its vastness pressing against the edges of thought. The universe is currently 13.8 billion years old. That's the time since the Big Bang, since space and time began expanding from an infinitely hot, infinitely dense point. 13.8 billion years. It sounds enormous, and it is by human standards. Our species has existed for maybe 300,000 years. Recorded history spans only about 5,000. In cosmic terms, we're newborns. Civilizations rise and fall in what amounts to a single tick of the universal clock. But 13.8 billion years, vast as it is, represents only the opening chapter of the cosmos. The universe is young, shockingly young. and the future stretches ahead for time spans that make the past look like nothing. Scientists estimate that a white dwarf needs between 10 quadrillion and 100 quintillion years to cool into a black dwarf. Let's sit with those numbers. 10 quadrillion is 10 to the 15th power, A1 followed by 15 zeros. 100 quintillion is 10 to the 20th power, a 1 followed by 20 zeros. To put that in perspective, if the entire current age of the universe, all 13.8 billion years, were compressed into a single second, then 1 quadrillion years would be roughly 72,000 years. And that's just 1 quadrillion. We're talking about 10, maybe 100 quadrillion years, maybe more. The exact number depends on the white dwarf's mass composition and initial temperature, but the range is staggering, no matter how you calculate it. It's time on a scale that makes geological epochs look instantaneous. Why does it take so long? The answer lies in the cooling curve we discussed earlier. A white dwarf radiates energy at a rate proportional to the 4th power of its temperature, which means the cooler it gets, the slower it loses heat. In the beginning, when the surface is 100,000 Kelvin, the dwarf sheds energy relatively quickly. But as it cools to 10,000 Kelvin, the rate drops dramatically. At 1,000 Kelvin, it's slower still. And as the temperature approaches the cosmic microwave background, currently 2.7 Kelvin, the rate of cooling becomes glacial, exponentially slower with each passing eon. The dwarf is asymptotically approaching thermal equilibrium with the void, but it never quite gets there, not in any time frame that matters to us. Let's try another comparison. The oldest known white dwarf in our galaxy is roughly 11 billion years old. It's been cooling since before the sun even formed. And yet, its surface temperature is still around 4,000 Kelvin. It's still glowing faintly in infrared, still radiating, still warm relatively speaking. It has been cooling for nearly the entire age of the universe, and it hasn't even come close to becoming a black dwarf. It has quadrillions of years left to go. Imagine that. An object that has existed since the universe was barely 3 billion years old, and it's still only in the early stages of its cooling journey. That's the patience required. That's the time scale. Here's a thought experiment that might help, though help is a generous word. Imagine you could watch a white dwarf cool in real time. You set up a telescope pointed at a nearby dwarf and start observing. How long would you have to watch before you noticed a measurable change in temperature? Research shows that a typical white dwarf cools at a rate of roughly 1 Kelvin every million years in its later stages. That's 1 degree for every million trips around the sun. If you watch for an entire human lifetime, 80 years, the temperature would drop by less than a 10,000th of a degree. You wouldn't notice. Not with the naked eye, not with instruments. You'd see nothing. No change, just a faint steady glow, indistinguishable from what it was when you started. To see meaningful cooling, you'd need to watch for millions of years, billions even. You'd need to be as patient as the star itself. And yet, even millions or billions of years are nothing compared to the full journey. Those are merely the early stages. The real wait, the wait for a white dwarf to cool from thousands of Kelvin down to single-digit temperatures, down to the temperature of the cosmic microwave background, down to the point where it could reasonably be called a black dwarf. That wait requires quadrillions of years. It requires a universe far older, far colder, far emptier than the one we inhabit. It requires conditions that don't exist yet, and won't exist for timescales so long that even saying won't exist for a long time feels absurd. They won't exist for an eternity, and then some. Cosmologists divide the universe's timeline into eras, each characterized by the dominant processes and objects. The first era, the one we're in now, is called the stelliferous era, the age of stars. This is when star formation is active, when galaxies are still bright with newborn suns, when fusion is happening on a massive scale across the cosmos. Scientists suggest the stelliferous era will last roughly 100 trillion years, 10 to the 14th power. That's the time it will take for the universe to exhaust its supply of hydrogen gas, the fuel that stars need to form. After that, no new stars will be born. The last red dwarfs, tiny long-lived stars that burn their fuel, slowly will flicker out, and the universe will enter the degenerate era. The degenerate era is the age of stellar remnants, white dwarfs, neutron stars, black holes. These are the objects that remain after stars die, and they're all that will be left once star formation ceases. The galaxies will be dark, their stars long since burned out or exploded. Only these remnants will remain drifting through space, slowly losing energy. White dwarfs will continue their patient cooling, edging closer and closer to becoming black dwarfs. Neutron stars will cool as well, though they follow a different path. Black holes will sit in the darkness, accreting the occasional bit of matter, growing imperceptibly larger. This era lasts from 10 to the 14th years to 10 to the 40 years, a span so vast, it makes the stelliferous era look like an eye blink. And it's during this era, in its later stages, that the first black dwarfs will finally appear. 10 to the 15th years, 10 to the 20th years. Let's try to ground those numbers in anything. If you counted one number per second without stopping, it would take you roughly 32,000 years to count to 1 trillion. To count to a quadrillion, 1,000 trillion would take 32 million years. And we're talking about 10 quadrillion, 100 quadrillion. Numbers so large that counting them is physically impossible. Even if every human who ever lived spent their entire life counting, we wouldn't scratch the surface. The numbers are beyond counting, beyond analogy, beyond comprehension. They exist only in the abstract, in the clean certainty of mathematics. And here's the truly unsettling part. Even those numbers might be underestimates. Some models suggest that under certain conditions, cooling could take even longer. If a white dwarf is particularly massive, if it has a thick hydrogen envelope, if neutrino emission is less efficient than predicted, the cooling time stretches. 10 to the 21st years, 10 to the 22nd. The uncertainty itself is vast, spanning orders of magnitude. We're not sure, not precisely because we've never observed a black dwarf. We've never seen the endpoint. We're extrapolating from theory, from models, from the physics we think we understand. But the universe has a way of surprising us. It's possible, likely even, that our current estimates are wrong. Maybe cooling takes longer than we think. Maybe it takes less time. We won't know until we can observe it directly, and that won't happen for quadrillions of years. What does it mean to wait that long? What does patience mean on that scale? For humans, patience is waiting for water to boil, for traffic to clear, for a season to change. We struggle to wait months. Years are hard. Decades feel impossible. But the universe doesn't struggle. It doesn't feel impatient. It simply unfolds second by second, year by year, eon by eon, following the laws of thermodynamics with perfect indifference. A white dwarf doesn't want to become a black dwarf. It doesn't strive or hope or anticipate. It just cools, automatically, inevitably. One photon at a time. There's something almost meditative in that, don't you think? The idea that change can be so slow, it's nearly imperceptible, and yet it still happens. That even on timescales beyond comprehension, even when nothing seems to be moving, entropy is at work. Heat is spreading. Energy is dissipating. The universe is cooling degree by infinitesimal degree towards some distant equilibrium. And in that slow, patient cooling, there's a kind of grace, a kind of acceptance. The white dwarf doesn't resist. It doesn't cling to its warmth. It just lets go slowly over quadrillions of years until there's nothing left to release. Have you ever thought about what it would be like to experience time that slowly, to be a consciousness if such a thing were possible? Living through quadrillions of years, each second would stretch into millennia. Each breath would span the rise and fall of civilizations. A single thought might take 1 billion years to complete, and yet subjectively, time might feel the same. Fast or slow time is only ever now. The present moment is all we ever experience, whether that moment lasts a second or a trillion years. Maybe in some strange way, the white dwarf's experience of time, if it had one, wouldn't feel long at all. Just a slow, steady dimming, a gentle fade, a patient drift into stillness. But we're getting philosophical, and the physics is patient enough without us adding metaphysics on top. The point is this: the timescales required for black dwarfs to form are so vast, they redefine what we mean by long. They force us to reckon with the fact that the universe we know, the one filled with stars and galaxies and light, is temporary, fleeting even. The future is longer than the past by an incomprehensible margin. And in that future, the universe will be dark, cold, empty. Except for these remnants, these black dwarfs drifting silently through the void, holding their crystalline forms long after everything else has faded. And even they, patient as they are, will continue their journey into even stranger, colder states. States we'll explore as we drift deeper into the night, into the far edges of cosmic time, where even black dwarfs begin to change. Picture the universe at 10 to the 20th years. All the stars have gone out, every single one. The galaxies, those great spiral arms of light and dust we photograph and marvel at, have dispersed or merged into massive elliptical ghosts themselves, now dark and silent. There are no planets warmed by sunlight because there is no sunlight. No nebulae glowing with the birth of new stars because star formation ended trillions of years ago. The cosmic microwave background, that faint afterglow of the Big Bang, has been redshifted into nothingness by the relentless expansion of space. In this future, the universe is a cold black ocean, and drifting through that ocean alone and invisible are the black dwarfs. They are the loneliest objects in existence. Not because they feel loneliness, they don't feel anything, but because they are truly profoundly isolated. In the degenerate era, matter is spread so thin that the average distance between objects is incomprehensible. Galaxies, or what remains of them, are separated by voids billions of light years across. Within those remnant galaxies, the black dwarfs drift, each one separated from its nearest neighbor by distances that dwarf the scale of our current solar system. Light years, tens of light years, perhaps more. And there is no light to mark their positions, no glow, no heat signature, just mass silent and dark moving through the void on trajectories set billions of years earlier before the stars even died. In our current universe, space feels full. Look up on a clear night and you see stars, thousands of them scattered across the dome of the sky. Each one is a sun burning bright, sending photons racing across space. Even the darkness between stars isn't truly empty. There's gas, dust, radiation, magnetic fields. Space hums with activity, with energy, with the byproducts of fusion and supernovae and stellar winds. But in the degenerate era, that hum has faded to silence. The gas has been incorporated into stars and then expelled into diffuse clouds too thin to ever collapse again. The dust has drifted apart, atoms separated by kilometers, then light years. The radiation has redshifted into oblivion. What remains is emptiness on a scale we can barely fathom. And in that emptiness, the black dwarfs persist. Scientists suggest there will be trillions upon trillions of them, remnants of all the sun-like stars that ever lived. Our own sun will be one, though. By then, the concept of our sun will have lost all meaning. There will be no Earth, no record of humanity, no memory that life ever existed on a small blue planet orbiting a yellow star. Just a black dwarf drifting through the ruins of what was once the Milky Way, its trajectory carrying it nowhere, in particular, forever. And it won't be unique. Every sun-like star in the galaxy will have followed the same path, main sequence, red giant, white dwarf, black dwarf. Hundreds of billions of them, each one alone, each one dark. Here's something people often misunderstand. They assume black dwarfs will eventually collide, that over enough time, gravity will pull them together into clusters or even new structures. It's a reasonable assumption. Gravity is always attractive, always pulling. so shouldn't objects eventually clump? But the universe's expansion complicates things. Research shows that on scales larger than galaxy clusters, space itself is expanding, and that expansion is accelerating. Distant objects are being pushed apart faster than gravity can pull them together. This means that on cosmic scales, the universe is becoming less dense, not more. Structures that are gravitationally bound, like remnant galaxies, will stay together, but everything else will drift farther and farther apart. The voids will grow. The isolation will deepen. Within a remnant galaxy, black dwarfs might occasionally pass near each other. Two dwarfs on intersecting orbits might come within a few light years, perhaps even closer, but actual collisions, vanishingly rare. Space is vast, and even within a galaxy, the distances are enormous compared to the size of the objects. A black dwarf is roughly the size of Earth, about 13,000 kilometers in diameter. A galaxy, even a dispersed remnant galaxy, is thousands of light years across. The odds of two Earth-sized objects randomly colliding in a space that large over even quadrillions of years are astronomically small. They'll pass by each other separated by distances that make interaction impossible. Ships in the night, if ships could be infinitely patient and infinitely cold. And what about the black dwarfs themselves? What are they like, these objects that have forgotten light? Imagine approaching one if such a thing were possible in that distant future. You wouldn't see it from a distance. No glint, no reflection, because there's no light to reflect. You'd only know it was there by its gravity, a faint tug on your trajectory as you drifted closer. And if you somehow landed on its surface, what would you find? A sphere of crystallized carbon and oxygen, its surface temperature indistinguishable from the surrounding void, perhaps a fraction of a Kelvin barely above absolute zero. The surface would be smooth, featureless, frozen solid. No atmosphere, of course. No weather, no erosion, no geological activity. Just a dead crust of atoms locked into place by quantum forces, a relic of a star that burned billions of years earlier. Beneath that surface, the structure persists. The crystalline lattice we discussed, stretching from the outer layers down to the core, organized and orderly. The black dwarf's mass, roughly half that of our sun, compressed into a volume the size of a planet. The density is staggering. A teaspoon of material from the surface would weigh tons. Deeper and near the core, where the pressure is highest, the density is even greater. And yet, there's no collapse, no implosion. Electron degeneracy pressure holds everything in place, quantum mechanics refusing to let the star compress further. It's a stalemate frozen in time, a balance that will last. Well, we'll get to that. One detail worth contemplating, even in this dead state, the black dwarf retains angular momentum. It spins slowly on its axis. The rotation rate depends on the star's history, how fast it was spinning. As a white dwarf, how much angular momentum was lost to stellar winds and radiation. Most white dwarfs rotate slowly, with periods ranging from hours to days. A black dwarf would retain that rotation, perhaps slowing further over unimaginable timescales due to the emission of gravitational waves, but never stopping completely. So, picture it, a dark sphere rotating silently in the void, once every few hours or days, its surface passing through space with perfect regularity. A clock of sorts, though. There's no one to read it. There's also the question of what happens to binary systems. Many stars exist in pairs orbiting a common center of mass. When both stars in a binary system are sun-like, they'll both become white dwarfs, and eventually both will cool into black dwarfs. Will they remain bound? Research shows that yes, gravitational bonds are persistent. Two black dwarfs that were once a binary pair of white dwarfs will continue to orbit each other. Their trajectories locked by gravity spiraling inward infinitesimally slowly due to the emission of gravitational radiation. Over quadrillions of years, they might edge closer, their orbits tightening, but actual mergers would take even longer. And if they did eventually merge, the result would be a more massive black dwarf, perhaps briefly warmed by the collision, but ultimately still cold, still dark. just larger. Do black dwarfs interact with anything? In the degenerate era, there's almost nothing left to interact with. No gas clouds to accrete, no nearby stars to exchange energy with. Occasionally, a black dwarf might encounter a rogue planet, a frozen world that was ejected from its solar system billions of years earlier, drifting through space like the dwarf itself. If the trajectories align, the planet might fall into orbit around the black dwarf, becoming a dark moon circling a dark sun. But even this is rare. Most black dwarfs will drift alone unaccompanied for the remainder of their existence. And yet, they're not entirely inert. Even at temperatures near absolute zero, quantum effects persist. The atoms in the crystalline lattice still vibrate, though the vibrations are minimal, constrained by the Heisenberg uncertainty principle. There's a zero-point energy, a fundamental restlessness that can't be eliminated even in the coldest possible state. The black dwarf hums faintly at the quantum level, a vibration that will never stop as long as the structure holds. It's not warmth, not in any meaningful sense, but it's motion. A reminder that even in the deepest cold, even in the most absolute stillness, matter is never truly at rest. Some people assume black dwarfs will eventually decay, that over enough time the atoms themselves will break down and the dwarf will dissolve into radiation. It's not an unreasonable thought after all. If protons decay, which some theories suggest they might, then the matter that makes up the black dwarf would eventually disintegrate. But proton decay, if it happens at all, operates on time scales of 10 to the 34th years or longer. That's far beyond the time required for black dwarfs to form, but still within the realm of deep future physics. We'll explore that possibility later. For now, in the degenerate era, the black dwarfs remain intact, solid, persistent. Monuments to a universe that once blazed with light. What does it mean to exist in such a state? To be a massive object holding form and structure, but contributing nothing to the universe around you. No light to warm a planet. No gravity strong enough to capture passing matter. No energy to give. Just existence for its own sake, without purpose or function. It's a kind of cosmic retirement, isn't it? The star has done its work. It fused hydrogen, created heavier elements, perhaps warmed planets, perhaps sustained life. And now it rests utterly and completely asking nothing, giving nothing, simply being. There's a strange comfort in that, I think. The idea that even when the work is done, even when there's nothing left to contribute, existence continues. The black dwarf doesn't need to justify itself. It doesn't need to be useful or productive. It just drifts patient and cold, holding its shape through sheer persistence. And maybe that's enough. Maybe existence itself, divorced from purpose or meaning, has its own quiet value. A value that doesn't need to be witnessed or acknowledged. A value that simply is. These are the loneliest objects, yes, but loneliness implies a lack, a desire for companionship. Black dwarfs don't lack anything. They don't desire. They're complete, in a sense, fully realized endpoints of stellar evolution, resting in the structure they earned through billions of years of fusion and cooling. And as we drift alongside them through this dark, empty future, we begin to wonder, is this truly the end? Or is there something beyond even this? Something stranger, colder, more final. Transformations that occur on time scales even longer than the wait for darkness. Changes that require not just the death of stars, but the decay of matter itself. Beyond the darkness, beyond the cold, beyond even the patient drift of black dwarfs through empty space, there lies a possibility. Stranger still. A transformation so slow, so improbable that it makes everything we've discussed so far seem hurried by comparison. It's called the iron star hypothesis, and it hinges on a single question that physicists have been asking for. Decades do protons decay? If they do, if the very building blocks of atomic nuclei are unstable over long enough timescales, then black dwarfs won't remain black dwarfs forever. They'll transform atom by atom into something even more stable, even more final. They'll become iron stars. Let's start with the basics. Everything around you, your body, the air, the ground, the stars, is made of atoms. And atoms are made of protons, neutrons, and electrons. Protons and neutrons cluster together in the nucleus, held by the strong nuclear force, while electrons orbit in clouds determined by quantum mechanics. For most of physics history, protons were assumed to be stable, permanent, eternal. A proton once formed would exist forever, barring interactions with other particles that might transform it into something else. But in the 1970s, certain theories in particle physics, grand unified theories, their call began to suggest that protons might not be stable after all. They might decay very slowly into lighter particles, positrons, photons, neutrinos. The process would be extraordinarily rare, with a half-life estimated at 10 to the 34th years or longer. But if it happens, it has profound implications for the far future, 10 to the 34th years. Let's pause and appreciate that number. It's a 1 followed by 34 zeros. To put it in perspective, the current age of the universe is about 10 to the 10th years, 10 billion. Proton decay operates on a time scale 10 trillion times longer than the entire history of the cosmos so far. If you set up an experiment to watch a single proton waiting for it to decay, you'd be waiting an unimaginable span of time. In fact, physicists have set up such experiments, massive tanks of ultra-pure water surrounded by detectors designed to catch the flash of light that would signal a proton's demise. They've been running for decades, watching trillions upon trillions of protons, and so far they've seen nothing. No decay, no signal. Protons, if they decay at all, are extraordinarily stable. But absence of evidence isn't evidence of absence, as the saying goes. Just because we haven't observed proton decay doesn't mean it doesn't happen. It might simply be too rare for current experiments to detect. And if it does happen, even at the glacial pace suggested by theory, it will eventually reshape every atom in the universe, including the atoms in black dwarfs. Research shows that if protons decay with a half-life of 10 to the 34th years, a typical black dwarf would lose a significant fraction of its mass over timescales of 10 to the 37th or 10 to the 40th years. Not quickly, not dramatically. Just slowly, steadily, as individual protons in the carbon and oxygen nuclei disintegrate, releasing energy and leaving behind lighter particles. What happens to a black dwarf when its protons start decaying? The process is gradual. A single proton decay event releases a tiny amount of energy, about 1 billion electron volts, which sounds like a lot, but is actually minuscule on macroscopic scales. That energy is deposited into the surrounding matter as heat. One decay, one photon, one slight increase in temperature. Over billions upon billions of years, as more and more protons decay, the cumulative effect begins to warm the black dwarf. Scientists suggest that this heating paradoxically could make the dwarf glow faintly again. Not with the bright light of a living star, but with a dim, ghostly luminescence powered not by fusion, but by the disintegration of matter itself. A zombie star, if you will. Glowing faintly in the deep darkness, not because it's alive, but because it's falling apart. But the heating is only temporary. As the protons decay the nuclei, they were part of become unstable. Carbon-12, which has 6 protons and 6 neutrons, loses a proton and becomes something else, perhaps boron-11, which is itself unstable and decays further. Over time, the complex nuclei that make up the black dwarf carbon, oxygen, neon, magnesium are broken down into simpler, more stable forms. And the most stable nucleus of all, the one with the lowest energy per nucleon, is iron-56. It has 26 protons and 30 neutrons arranged in a configuration so stable that neither fusion nor fission can extract energy from it. Iron-56 is the ultimate endpoint of nuclear stability. It's the ash that remains when all other nuclear processes have run their course. This is where the term iron star comes from. If proton decay occurs, and if it proceeds long enough, the black dwarf's composition will gradually shift. The carbon and oxygen lattice will decay proton by proton, and the debris will eventually settle into iron. The process is called cold fusion, though that term is misleading. It's not fusion in the traditional sense, where nuclei are smashed together at high temperatures. Instead, it's a slow rearrangement driven by quantum tunneling and proton decay occurring over time scales, so vast they make the age of the universe look like a microsecond. Scientists suggest the transition from black dwarf to iron star would take roughly 10 to the 1500 years. That's 10 to the power of 1500. A number so large it has no name, no analogy, no comprehensible scale. It's a number that exists only in the abstract, a placeholder for unimaginably far in the future. But let's assume it happens. Let's imagine a universe at 10 to the 1500 years long after proton decay has run its course. What remains iron stars. Spheres of solid iron roughly the size of planets, drifting through a void even emptier and darker than the one we have already described. They're colder than the black dwarfs that preceded them, because by this point, the universe's expansion will have redshifted the cosmic microwave background to temperatures indistinguishable from absolute zero. The iron stars will sit at that temperature, or as close to it as quantum mechanics allows, held up by the same electron degeneracy pressure that supported the black dwarfs. They won't glow, they won't radiate. They'll just exist silent monuments to a universe that once knew light. Iron is strange stuff, especially in this context. Here on Earth, iron is common. It's the fourth most abundant element in the crust, the metal we use for buildings and bridges and tools. It rusts, corrodes, reacts with oxygen. But in an iron star, there's no oxygen to react with. No water, no atmosphere. Just pure iron crystallized into a lattice held at near absolute zero temperatures. The structure would be different from terrestrial iron. The extreme pressure inside the star would create phases of iron that don't exist on Earth, exotic crystalline forms, with properties we can only guess at. And unlike the carbon-oxygen lattice of a black dwarf, which has some aesthetic appeal, diamond after all is beautiful, iron feels more mundane, duller. The final state of stellar evolution is a ball of rust-colored metal, frozen and forgotten in the void. Here's something people often get wrong. They assume iron stars would be magnetic. After all, iron is famously magnetic here on Earth. But magnetism requires electron spin alignment, and in the degenerate matter of a stellar remnant, electrons are in such extreme quantum states that traditional magnetism doesn't really apply. Some models suggest iron stars could have weak magnetic fields, remnants of the white dwarf's original field, but they wouldn't be the powerful magnets you might imagine. Just cold, dense spheres of iron, no more magnetic than any other degenerate object. And there's another complication: we're not even sure proton decay happens. Despite decades of searching, despite increasingly sensitive experiments, we've never observed a single proton decaying. The current lower limit on the proton's half-life based on experimental data is about 10 to the 34th years. But that's a lower limit. The actual half-life could be longer, much longer. It could be 10 to the 40 years, 10 to the 50, or protons could be completely stable, lasting forever without decay. If protons don't decay, then black dwarfs won't become iron stars. They'll remain black dwarfs, carbon and oxygen crystals drifting through the void for eternity, or at least for as long as eternity has meaning in a universe governed by quantum mechanics. But let's assume, for the sake of exploring the furthest reaches of possibility, that protons do decay. What then? The transformation from black dwarf to iron star is just one more step in a long chain of transformations. Hydrogen cloud to star to red, giant, red, giant to white, white dwarf to black dwarf to iron star. Each step takes longer than the one before. Each state is colder, darker, more stable. It's a journey toward ultimate equilibrium, toward the lowest possible energy state, toward a universe where nothing changes, because there's no energy left to drive change. Physicists call this the heat death of the universe, a state where entropy has reached its maximum, where all energy has been evenly distributed, where no work can be done, no processes can occur, just stillness stretching on forever. The iron star represents something close to that endpoint, at least for stellar remnants. It's as low as you can go in terms of nuclear energy. Iron 56 cannot be fused into heavier elements without adding energy, and it cannot be split into lighter elements without adding energy. It's the bottom of the nuclear valley, the most stable configuration of protons and neutrons. In a sense, iron stars are the universe's way of saying, this is as stable as matter can get. This is the end. And yet even iron stars might not be the final word. Even they, given enough time, and we're talking time scales beyond, even 10 to the 1500 years, might succumb to even stranger quantum processes. Processes we'll explore as we drift further into the abyss of deep time. But there's something almost peaceful in the iron star hypothesis, don't you think? The idea that even after everything has decayed, even after the atoms themselves have fallen apart, there's still structure, still form. The universe doesn't dissolve into chaos. It transforms step by patient step into something simpler, something more stable, something that can rest without change. And in that rest, there's a kind of finality. Not an ending in the dramatic sense, but a settling, a cosmic exhale. The universe having run through all its transformations, finally finding a state where it can simply be. Of course, this assumes proton decay. And it assumes the universe continues expanding, cooling, thinning into the void. There are other possibilities, scenarios involving quantum tunneling, vacuum decay, the slow evaporation of matter itself through mechanisms even stranger than proton decay. And those possibilities, those final transformations, await us in the deepest reaches of time, where even iron stars might begin to fade. What happens when even stillness isn't final? When even the most stable objects in the universe, black dwarfs, iron stars, the cold remnants of a cosmos that once blazed, begin to evaporate, not through decay, not through collision, but through a quantum whisper so faint it takes longer than infinity seems to allow. This is the realm of Hawking radiation, a process so slow, so improbable, that it makes everything we've discussed feel instantaneous. And yet, it's real as gravity, as certain as entropy. Even black dwarfs will eventually dissolve into nothing, one particle at a time, over time scales that redefine what we mean by forever. Hawking radiation was proposed by physicist Stephen Hawking in 1974 in the context of black holes. The idea is rooted in quantum mechanics and general relativity working together in strange ways. Near the event horizon of a black hole, quantum fluctuations in the vacuum create pairs of virtual particles, one particle and one antiparticle that normally annihilate each other almost instantly. But at the event horizon, something peculiar happens. One particle falls into the black hole, while the other escapes into space. The escaping particle becomes real, carrying away a tiny amount of energy. From the outside, it looks like the black hole is radiating particles glowing in a sense, even though black holes, by definition, don't emit anything. This radiation, this quantum leak, causes the black hole to lose mass over time, slowly, imperceptibly, but inevitably. For stellar mass black holes, the kind formed from supernova explosions. Hawking radiation is negligible. A black hole with 10 times the mass of the Sun would take about 10 to the 67th years to evaporate completely. That's a 1 followed by 67 zeros, a timescale so vast it dwarfs even the proton decay scenarios we discussed. But here's the twist. Hawking radiation isn't limited to black holes. Any object with mass in principle emits this quantum radiation, though the rate depends on the object's properties. Smaller, less massive objects radiate faster. Larger, more massive objects radiate slower. And for something like a black dwarf, a stellar remnant with about half the sun's mass compressed into the size of Earth. The timescale for evaporation is almost incomprehensibly long. Scientists suggest a black dwarf would take roughly 10 to the 100th years to evaporate via Hawking radiation. 10 to the 100th. Let's sit with that. It's a number so large that writing it out in full would require 100 zeros. For comparison, the number of atoms in the observable universe is estimated at around 10 to the 80th. The timescale for black dwarf evaporation exceeds the number of atoms in existence. It's a Google years. The term Google itself was coined to describe this kind of absurdly large number, and then some. If you tried to count to 10 to the 100th one number per second, you'd be counting for longer than 10 to the 92nd years. It's a recursion of impossibility, a number that exists only in the mathematical sense, far beyond anything we can visualize or experience. But the physics is sound. Research shows that even at near absolute zero temperatures, quantum fluctuations at the surface of a black dwarf would create particle-antiparticle pairs, and occasionally one particle would escape while the other falls back into the dwarf. Each escaping particle carries away a minuscule amount of mass energy as dictated by Einstein's equation. Over time, unimaginable time, the black dwarf shrinks. Atom by atom, proton by proton, electron by electron, it radiates itself into oblivion. The process accelerates as the dwarf becomes smaller, because smaller objects radiate faster. In the final moments, the last remnants of the black dwarf would glow briefly, not with visible light, but with high-energy gamma rays before disappearing entirely in a final quantum sigh. What does this evaporation look like? Imagine watching a black dwarf over 10 to the 100th years time-lapse style. For the first 10 to the 99th years, nothing visible happens. The dwarf sits in the void, dark, and still emitting radiation at a rate so slow it's effectively zero. Its mass decreases by infinitesimal fractions, undetectable even by the most precise instruments. But eventually, after eons beyond counting, the mass begins to drop noticeably. The dwarf shrinks its radius, decreasing its density, paradoxically increasing as it loses outer layers. The rate of radiation climbs. After 10 to the 99.9 years, the process accelerates. The dwarf, now perhaps the size of a mountain, glows faintly in gamma rays. After 10 to the 99.99 years, it's the size of a building, radiating fiercely, its temperature climbing as it shrinks. And in the final microseconds relative to the total time scale, it flashes once brightly and vanishes. Not into a black hole, not into collapse, just into photons, neutrinos, and perhaps a few exotic particles dispersed into the void. Here's where people often misunderstand. They assume Hawking radiation only applies to black holes, or that it's somehow different for other objects. It's not. The mechanism is the same. Quantum fluctuations near a gravitational field create particle pairs, and occasionally one escapes. The difference is in the rate. Black holes with their intense gravity concentrated at the event horizon radiate faster than most objects. Black dwarfs with their weaker gravity spread over a larger surface radiate slower, but the principle is identical. Everything with mass, given enough time, will evaporate. Everything. This includes iron stars if they exist. If proton decay has transformed black dwarfs into spheres of iron, those iron stars will also emit Hawking radiation at roughly the same rate as the black dwarfs that preceded them. The composition doesn't matter much. What matters is mass density and surface gravity. An iron star would take 10 to the 100th years to evaporate just like a black dwarf. The universe in this sense is patient but thorough. It erases everything given enough time. And what about black holes themselves? We mentioned earlier that stellar mass black holes evaporate on timescales of 10 to the 67th years. Supermassive black holes, the kind at the centers of galaxies with millions or billions of solar masses, take even longer. The largest black holes we know, with tens of billions of solar masses, would take roughly 10 to the 100th years to evaporate. Interestingly, this is roughly the same time scale as black dwarf evaporation. So in the deepest reaches of time, black holes and black dwarfs are evaporating simultaneously, both fading into radiation, both contributing their mass energy back to the void. It's a cosmic symmetry, a parallel ending for objects that began their lives in completely different ways. One detail worth noting: as black dwarfs evaporate, they don't just disappear smoothly. The process is probabilistic, governed by quantum mechanics, which means it's inherently random. Some particles escape early, others late. The dwarf's mass decreases in fits and starts a stuttering decay rather than a smooth curve. And in the final stages, when the dwarf is small enough that quantum effects dominate the structure itself, becomes uncertain. The crystalline lattice, which held for quadrillions of years, begins to blur. Atoms are no longer in definite positions. The boundary between the dwarf and the surrounding vacuum becomes fuzzy. It's no longer a classical object with well-defined edges. It's a quantum superposition, a probability cloud that gradually disperses into the void. What remains when the evaporation is complete? Photons, mostly. High-energy gamma rays carrying the dwarf's mass energy, spreading outward at the speed of light. Neutrinos, ghostly particles that interact with almost nothing, racing through space unimpeded. Perhaps a few gravitons if quantum gravity behaves the way some theories suggest. But no matter. No atoms, no nuclei, no electrons. The dwarf, which once was a star which fused hydrogen into helium and helium into carbon and oxygen, which cooled for quadrillions of years, which crystallized into diamond and perhaps transformed into iron, has become pure energy. Dispersed, diluted, indistinguishable from the background radiation of an infinitely old, infinitely cold universe. And here's the final twist: even that radiation doesn't last. The photons, the neutrinos, the particles that were once the black dwarf are subject to the universe's expansion. As space stretches, their wavelengths stretch too redshifting into lower and lower energies. A gamma ray becomes an X-ray, then ultraviolet, then visible, then infrared, then microwave, then radio. Eventually, the wavelength becomes so long, perhaps light years, perhaps larger than the observable universe itself, that the photon ceases to carry meaningful energy. It becomes indistinguishable from the vacuum fluctuations from the quantum foam that permeates space. And at that point, even the memory of the black dwarf is gone, completely, utterly, as if it never existed. This is the heat death of the universe in its purest form. Not a dramatic explosion, not a cosmic crunch, but a slow, patient dissolution of everything into nothing. Every black dwarf evaporates. Every black hole evaporates. Every particle redshifts into irrelevance. The universe becomes a cold, dark, empty expanse with no structure, no gradients, no differences in temperature or density. Just quantum vacuum fluctuating randomly, stretching on forever. And in that state, time itself loses meaning. There's no change, no process, no events to mark the passage of moments. Just stillness. Eternal, absolute stillness. Do you ever think about what it means for something to truly end? Not just to stop functioning, but to cease existing in any form. We're used to conservation laws. Energy is conserved. Mass is conserved. Nothing is truly destroyed, only transformed. But in the far future, after Hawking radiation has run its course, even that conservation feels hollow. The energy still exists technically, but it's spread so thin, redshifted so far, that it might as well not. The universe remembers nothing. Not the stars, not the galaxies, not the black dwarfs that once drifted through the void. Everything has been erased, returned to the formless potential from which it came. And yet, there's a strange beauty in that, isn't there? The idea that the universe, having explored every possible structure, every configuration of matter and energy, Every transformation from hydrogen to helium to carbon to iron to photons finally rests. Not in sleep. Sleep implies the possibility of waking, but in completion. The universe has done all it can do. It has burned, cooled, crystallized, decayed, evaporated. And now it simply is. Without change, without future, without memory. A perfect equilibrium, a perfect stillness. And in that stillness, perhaps there's a kind of peace that we, with our brief, bright lives, can only glimpse from a distance as we drift through these final thoughts toward our own quiet ending. We've traveled far tonight, farther than light could carry us in 1 billion lifetimes, farther than thought usually dares to go. We started with a question: what happens to stars when even the last embers forget how to glow? And we followed that question through the deep architecture of time, through white dwarfs cooling in the darkness, through crystallization, that strange alchemy where stars become jewels, through time scales so vast they make eternity feel intimate, through loneliness and decay, through iron and evaporation, all the way to the edge of existence itself, where even matter whispers itself into nothingness. Black dwarfs don't exist yet, not a single one anywhere in the universe. And they won't exist for quadrillions of years, long after our sun has died, long after the Milky Way has merged with Andromeda and gone dark, long after the last stars have flickered out and the cosmos has grown cold and still. But in some profound way, they already matter. They tell us something essential about the universe's character, about its patience, about the way it holds form, even in the deepest cold, and then eventually lets go. There's a lesson in that, though maybe lesson isn't quite the right word. An observation, a meditation. The universe doesn't cling. It transforms step by patient step, from hydrogen clouds to stars, from stars to remnants, from remnants to radiation, from radiation to silence. Each phase lasts longer than the one before. Each state is colder, darker, more still. And at every stage, there's a kind of dignity in the process. The star doesn't resist becoming a white dwarf. The white dwarf doesn't fight against cooling. The black dwarf doesn't struggle against evaporation. It just happens naturally, inevitably following the laws written into the fabric of reality. We humans have a complicated relationship with endings. We build monuments to resist them, write stories to outlast them, search for immortality in children, in art, in memory. We want to matter. We want to persist. And there's nothing wrong with that. It's part of what makes us human, this refusal to quietly fade. But the universe offers a different perspective. It shows us that endings aren't failures, they're completions. The star that becomes a black dwarf hasn't failed, it's finished. It's done its work, fused its hydrogen, warmed its planets, created the heavy elements that make life possible. And now, it rests as having earned its stillness through billions of years of burning. Think about our sun for a moment. Right now, it's middle-aged stable, fusing hydrogen into helium at a steady rate, warming Earth and the other planets in our solar system. In about 5 billion years, it will swell into a red giant, its outer layers expanding to engulf the inner planets. Mercury will be consumed. Venus, too. Earth might survive scorched and lifeless, or it might not. Either way, the sun, we know, will be gone. What remains will be a white dwarf no larger than Earth, glowing faintly in the void. And over the next quadrillion years, that white dwarf will cool degree by imperceptible degree until it becomes a black dwarf, our sun's final form. A crystalline sphere of carbon and oxygen drifting silently through a universe that has forgotten light. Does that make you sad? It used to make me feel a kind of cosmic melancholy, the idea that something as warm and life-giving as the sun would end that way. But over time, my perspective shifted. Because the sun's journey isn't a tragedy, it's a fulfillment. The sun is doing exactly what stars do. It's following the script written by physics, playing its role in the great cycle of matter and energy. And when it finally becomes a black dwarf, it won't be diminished. It will be complete, a finished work, a star that lived fully, that gave everything it had, and now rests in the structure it earned. And there's something beautiful in that structure, isn't there? We talked about crystallization, the way a cooling white dwarf's interior organizes itself into a diamond-like lattice. That's not decay, that's organization. That's the universe creating order out of chaos, finding patterns even in death. The black dwarf, for all its coldness and darkness, is one of the most organized objects imaginable. Every atom in its place locked into a quantum lattice that will persist for eons. It's a monument to what the star once was, a memory held not in neurons or hard drives, but in the arrangement of carbon and oxygen nuclei frozen into geometry. We also explored the possibility of iron stars, those hypothetical endpoints where proton decay transforms carbon and oxygen into the most stable element in the universe, iron 56, the nuclear ground state, the element that can neither fuse nor fission to release energy. If black dwarfs become iron stars, they're taking one more step toward ultimate stability. They're finding the lowest energy state, the configuration where nothing more can change. And then, after timescales that exceed even that transformation, Hawking radiation whispers them away, particle by particle, until nothing remains but photons dispersed across an infinite void. It's easy to look at that final evaporation and see it as erasure, as the universe forgetting everything that ever was. And in a literal sense, that's true. The black dwarf evaporates the photons, redshift the energy spreads thin until it's indistinguishable from the vacuum. But here's another way to think about it. The black dwarf's mass energy doesn't disappear, it transforms. It becomes light radiation, a faint contribution to the background hum of the cosmos. The star gave warmth for billions of years during its main sequence life. It gave structure for quadrillions of years as a black dwarf. And in its final act, it gives itself entirely dissolving into the universe, becoming part of the whole. That's not loss. That's generosity on a cosmic scale. Scientists sometimes talk about the heat death of the universe, the state where entropy has maximized, where all energy gradients have smoothed out, where nothing can happen because there's no energy differential to drive change. It sounds grim, doesn't it? Heat death, the end of everything. But maybe it's not death in the tragic sense. Maybe it's rest. The universe having explored every possible configuration, every dance of matter and energy finally settling into equilibrium. No more struggle, no more transformation, just stillness, perfect and complete. And you know what's remarkable? We're here to contemplate it. Right now, in this brief bright window of cosmic history, we exist. Conscious beings made of stardust, thinking about the far future, about black dwarfs that won't exist for quadrillions of years. Our lives are fleeting 100 years, if we're lucky, a cosmic eye blink. And yet, in that eye blink, we can grasp these vast timescales. We can follow the mathematics, the physics, the logic of stellar evolution, all the way to its conclusion. We can stand in the present and imagine the deepest future, and in doing so, we touch something eternal. That's the gift of science, I think. Not just knowledge, but perspective. The ability to see ourselves in context, to understand that we're part of something much larger, much older, much more patient than our individual lives. The atoms in your body were forged in stars that died before the sun was born. The carbon in your cells, the oxygen you breathe, the iron in your blood, all of it came from stellar fusion, from stars that lived and died and gave their substance to the universe. And someday, those atoms will return to the cosmos. Maybe they'll be part of a new star, a new planet, a new form of life. Or maybe they'll drift in the void until proton decay claims them, transforming them into iron, into photons, into nothing. Either way, they'll continue the cycle. We've spent over an hour and a half together tonight, drifting through these deep, quiet places where time moves differently and light is just a memory. We started with black dwarfs, objects that don't exist yet, and we traced their lineage back through white dwarfs, red giants, main sequence stars, all the way to the hydrogen clouds where stars are born. We explored the physics of cooling, the mystery of crystallization, the mathematics of deep time. We contemplated loneliness and stillness, decay and evaporation, the slow march toward entropy. And through it all, we found not despair, but a kind of peace. Because the universe isn't cruel, it's patient. It allows stars to burn for billions of years, to create the elements necessary for life to warm planets to light the void. And when their fuel is exhausted, it allows them to rest. Slowly, gently over time scales so long, they redefine patience. The white dwarf cools, the black dwarf drifts. The iron star persists, and eventually, after eons beyond counting, even they dissolve, returning their energy to the cosmos. It's a cycle, ancient and ongoing, and we're part of it. Right now, in this moment, we're the universe looking at itself, understanding itself, marveling at its own deep patterns. So, what do we take from this? What does it mean to know that black dwarfs will one day exist and then one day evaporate, and that the universe will continue cold and dark and empty forever? Maybe it means that endings aren't something to fear. They're something to accept, to honor, to see as natural completions rather than failures. The star ends. We end. Civilizations end. But the universe continues and the patterns persist, and the laws that govern everything, thermodynamics, quantum mechanics, relativity, remain true, elegant and indifferent. Or maybe it means something simpler. Maybe it means that here now, in this brief flicker of warmth and light, we should pay attention. We should notice the stars while they're still shining. We should appreciate the fact that we exist in the stelliferous era, the age of light when galaxies still glow and fusion still happens, and the universe is young enough to be interesting. Because this won't last, not forever. And someday far in the future, there will be no one left to look up at the night sky and see stars. There will only be darkness and silence and the patient drift of black dwarfs through the void. But that's not now. Now we have light. We have warmth. We have each other briefly in this shared moment of contemplation. And that's enough. More than enough, it's everything. Thank you for drifting with me tonight. Thank you for sitting with these vast time scales, these deep questions, these quiet transformations. Thank you for caring about black dwarfs, about the far future, about the universe's slow journey towards stillness. It's been an honor to share this space with you, to whisper these thoughts into the dark and know that you're listening. If you found comfort in this journey, if these ideas resonated with you in some quiet way, I'd be grateful if you'd share this video with someone who might need it. Someone who looks up at the stars and wonders. Someone who finds peace in deep time and cosmic perspective. And if you'd like to continue exploring these nocturnal wanderings with me, there are more stories waiting, more mysteries to unfold, more gentle dives into the nature of reality. I'll be here whenever you need a quiet voice in the stillness. Sleep well. Dream gently. And remember, even in darkness, even in the deepest cold, the universe still holds you. The same quantum rules that support black dwarfs support you. The same atoms that will one day become iron, and photons are right now part of you. You're not separate from this cosmic story. You're woven into it, a brief, bright thread in an infinite tapestry. And that's a beautiful thing. Good night, friend. Until the next quiet night finds us both.